in connection to Science Night. Please stand by.
Welcome back to another special episode of the Science Night podcast. Tonight, we're talking about the biggest stories in fusion energy from 2021 in our Festival of Fusion. My name is James, and with me tonight is, of course, Dr. Steffi Deem, because how are we going to talk about fusion without the person that, knows stuff about it? So thank you, Steffi, for helping us out tonight.
Thanks for joining us, James. I'm excited.
I am too. I'm especially excited because our special guest, Dr. Arturo Dominguez, the head of Science Education Department at the Princeton Plasma Physics Laboratory. I'm assuming that Princeton has a plasma physics laboratory because we don't have one here at Dartmouth. That must be the only reason. But Dr. Arturo Dominguez, thank you so much for joining us today.
Thanks, James. It's a pleasure to be here with y'all.
What we're going to do tonight is go through some of the biggest developments in fusion energy of 2021, and then after that, Dr. Steffi Deem is going to talk to Arturo about what he does and engagement with the public that he does to further fusion's goals in the public, or at least have people have a baseline idea of what's going on, because as you'll find out in 1 second, I do not have that baseline. So let us get started with the 2021 Fusion Energy Year in Review. And I am going to ask a question that I obviously have a very insightful and articulate answer to. But for the sake of our listeners that I love dearly, my question is, what is fusion?
That is a great question.
And obviously I could answer this right now, but I think maybe we'll let Arturo or Steffi take a shot at this.
We get it a lot, and I'm going to throw this over to Arturo.
All right. Yes. Fusion is what happens in the center of all the stars. When you have very small particles, in this case, the nuclei of hydrogen, which are just protons, when you get them close enough to each other that they overcome their repulsion and they are taken over by the nuclear strong force, you create bigger nuclei, which releases a lot of energy. At that microscopic scale, it's just kinetic energy of the nuclei, but it releases a lot of energy that results in radiation or in, pressure. So that's how the sun and the stars create the energy that they create. And the purpose of fusion energy on Earth is to recreate those processes in machines on Earth.
That is a much better answer than I was going to give, because I thought it was a Ford car. So I'm glad that we've established what we're talking about now. Obviously, this whole fusion energy thing is for the movies. It's not a thing that we're going to be able to achieve within the next 100,000 years, right? It's science fiction firmly, right?
Oh, it's coming. It's right around the horizon. There's been a lot going on in our field just in the past few years recently. So it's been historically a science program in the U.S. and all over the world. We have a lot of advantages right now that kind of push fusion out of the lab into reality to bring us ever closer to harnessing the power of fusion for commercial use. So I'll just highlight a couple of the technological advances we have now. We've gotten really good at making optimal conditions to confine the fuel for fusion here on Earth. And we'll talk a little bit about those devices later on. All these advances in additive and advanced manufacturing give us tools to do rapid prototyping for these experiments, to come up with materials to withstand these harsh environments. Computing capabilities are amazing now, so we can do highest level simulations. And we have all of this in interest from private industry. In particular, we'll talk about this later, high temperature superconducting magnets. They are coming online. Technology is here now, and they allow us to make more compact reactors. And I mentioned private industry. So I think at the beginning of 2021, we were sitting at like $2 billion invested in the private sector. Now close to $5 billion just in 1 year. Yeah.
That is a giant leap, I think we could say. I'm really excited to get into some of the things that we have brought online this year, but since we have firmly established we are not talking about the Ford fusion, I think we have to say, like, how do we do fusion on Earth? How do we do it here? I'm assuming we can't just click the start fusion. So Arturo, can you maybe shed a little bit of plasma light onto how we do fusion on Earth?
Yes, absolutely. So you just said a keyword, plasma, right? We always connect plasma and fusion, and it's not always entirely clear why. Plasma is the fourth state of matter. It's when you heat up a gas enough that you get the electrons torn off from the nuclei, and so you get a soup of positive ions and negative electrons all around. With my description of fusion, it kind of makes sense why you need that, right? Because you have the nuclei getting close together. But I didn't really say how we get those nuclei close together. As I said, they're both positive. They don't want to get close together. So what do? And the answer really is we make it very hot or we make it very dense. We make all of these positively charged nuclei, force them to be very close together. The idea of making it really hot, how you actually do that, making this hydrogen, in this case it's isotopes of hydrogen, that is one proton and different number of neutrons, but it's effectively hydrogen. You heat that up through microwaves or in some sort of electromagnetic radiation or bombarding it. You heat that up to temperatures hotter than the center of the sun. In truth, we need it to be about 10 times hotter than the center of the sun for our devices, right? So we do that on a pretty regular basis, heating it up by putting a lot of energy into very few particles of gas. The real question is, how do you contain it? Like Steffi said, we've done advancements in containment. How do you actually contain it? And one clue to it is the auroras, the northern lights, southern lights. You see when you go out to the very north or south, you see at night these light shows, which is plasma that's coming from the sun and going to the north and the south pole. Why do we only see it in the north and the south pole? Well, because the Earth is like a big magnet. And it turns out that when plasma gets close to magnetic fields, it gets stuck on magnetic fields and moves on it kind of like an ant on a guitar string. It can move along the guitar string, but not jump across it. So the plasma sees the magnetic fields and goes to the very north and the very south, interacts with the atmosphere, and glows. So all this to say that plasma, which is what we need for fusion, interacts with magnetic fields in a way that the magnetic fields can confine it, right? The magnetic fields can hold on to it. That's magnetic confinement. So what you can do is you can create a machine that looks kind of like a hollowed out donut, and you create a big magnetic field right down the middle. And you heat it up, as I said, with electromagnetic radiation or bombarding it with other atoms. And you heat it up, but the magnetic field makes sure that it stays away from the walls. That's the big idea of magnetic confinement. So when you look at, for example, the machine that Steffi is building in her lab, that looks like a hollow donut. It looks kind of like a cored apple, but it's that same topology. And that's magnetic confinement. Another big idea is, okay, what if we make a pellet, make a small ball of the fuel that we need, and what we do is we squeeze it really fast and make sure that you get to the very high density and to the high temperatures that you need for fusion while it compresses. And that's the idea of inertial confinement fusion. A big leader in this is the National Ignition Facility in Lawrence Livermore Labs. But this is the idea of inertial fusion. You collapse a small pellet by bombarding it with lasers or with some other force some other form of energy, and you compress it and make fusion happen there. So those are really the two main ways and variations of those that we do it here on Earth.
That was great, but I think one thing we do have to mention, just because I can see it on the document and I'm still having trouble wrapping my head around it, is what are the temperatures we are talking about here? So it's a little bit hotter than one can achieve with your Easy Bake Oven, which is the hottest substance that we can do on Earth right now is the light bulb of an Easy Bake Oven.
Right, exactly. So when we say 10 times hotter than the sun, we're talking hundreds of millions of degrees. I mean, this is super, super hot. They get really creative, which is what Arturo said, because the sun, we can't use the sun uses gravity. Fortunately, we don't have that here. So we have lasers and magnets.
Yeah. So when we're talking about why it's kind of difficult to do this, it's one of the reasons is it gets real hot, really hot, more than just opening windows could contain. So, yeah. So this is pretty insane. And so we've talked about we're kind of able to get up to this point, and there is a word that I think also warrants a bigger discussion, which is the break-even point. Why don't we talk about what the break-even point is? Because that's going to definitely help with the stories that we talk about in a little bit.
Yeah, so you'll probably see this in the news, break-even or ignited or burning. What that really means is that when you're harnessing fusion for energy, you want to get more energy out of the system than you put into it. So it's kind of that ratio of energy in over energy out. And so when you get more energy out of the system than you put in, you've achieved break-even. Where you put that boundary, you need to pay attention to that. So a lot of us, because we're working on science experiments, we're looking at how much energy actually gets into the device, not all of the energy that goes into the system. So that's something to keep into mind. The other thing I want to emphasize is a lot of times you'll see in these articles, why aren't we powering the grid? Why haven't we achieved break even yet? We haven't designed any experiments to achieve break even. That's by design, because we're always working on optimizing these conditions to confine the plasma. So there's going to be part of this, we'll talk a little bit. Some experiments are getting close. Some experiments are actually being designed and built and constructed to actually demonstrate that. So that's going to be really exciting to have that come online.
I think we're talking about how this is a difficult thing. It seems also like an expensive thing. So I'm going to ask you the question that you probably get a lot from a random person of the public that has no idea about fusion energy. Why are we doing this? Why? What's the point?
Well, why we're doing it is because we've got to do something. When you look at all the projections of climate change, and when you look at the cost to humanity of not finding alternatives that are going to power the world without emission of greenhouse gases, it sounds cliche, but we can't afford not to be looking at all of the alternatives that we can to deliver electricity into the grid, both here in the U.S. and worldwide, without creating greenhouse gases. And fusion has that ability. We haven't really talked about that, but when you create fusion, you don't have any greenhouse gases to worry about as a byproduct. The only byproduct is helium, like the one that you blow up balloons with. And it's very little of that even there. It's also very abundant. We have projections of hundreds of thousands of years of fusion energy if we can get it developed. So it really is an alternative energy source that could solve a lot of our problems. I always caution against saying it's the only one or it's the best one, because I don't think there's a best one. There are different ones for different occasions, but we need all of the tools in our toolkit to tackle climate change.
I'm just going to throw in this analogy I like to use. So this is looking at the energy for one human lifetime. And I'm going to do the comparison between fuel for fusion and fuel for coal. So we're looking at how much fuel from fusion to power everything in your lifetime. That's your computers, your house, your car, everything. You can get that from the deuterium, which is an isotope of hydrogen found in one bathtub, plus the tritium that can be bred from lithium of 2 laptop batteries. No pollution. That's amazing. And if you compare that to the coal equivalent, you would have to burn 230 tons of coal. And that in turn produces 380 tons of pollution. So this kind of goes back to what Arturo was saying. It could be a game changer when you're talking about climate change.
It seems like we're coming to the conclusion, as with all great sci-fi things that become just sci, is that these things become achievable when we decide that we should really start working on this and put some effort behind that, because all I've heard about fusion energy for my entire lifetime is that it is a pipe dream and it is a waste of time, and now we're like, oh man, the world is on fire. Here's this thing that will not create more fire to put on the world. Maybe we should put some effort. And now we have an entire podcast episode's worth of things that we can talk about that have happened in the past year. So, maybe we start to open those pocketbooks and things can happen for good this time.
It's in large part our community's fault for what has happened. I think in the past when people say, it's always 30 years away, that's on us. We have overpromised, especially at times when we really shouldn't. We shouldn't have been making these promises without building the machines and without putting our money where our mouth was. And it's come to haunt us because, as you say, a lot of people have heard about maybe cold fusion or maybe overpromised, a field that's been overpromised. I think that one big data point, as Steffi pointed out, is that a lot of people with a lot of money that are taking the time to do the research and looking into what are the promises being made are actually investing in this. This has gone outside the laboratory and into industry. And when you look at these industries, they have to be doing a holistic analysis of how you can get to actually electricity in the grid. And they're doing this and they're getting investment into it. That's one of the many data points. As you'll see from this discussion about this last year in fusion, that really supports the idea that it's a different time.
Well, now I think we at least have the bird's eye view of the basics of fusion so that we have a little bit of an idea what we're talking about. When we talk about the things that happened over the past year that have made fusion become closer than ever. So now I think it's time to cover those top stories of 2021. And I am going to let Steffi take control at this point and play the role I was born to do, the person who knows nothing about fusion.
Thanks, James. Just catch us on all our acronyms, please, and jargon.
I can do that.
Okay.
Thanks to my Alda Center training.
Yay. Okay, so we're going to start off 2021 with the U.S. fusion community came together to build consensus. And for me, this was kind of an eye-opening experience because we're all scientists, very passionate about our work. And how do you get everyone together to kind of focus, to come together to a shared vision or a mission of what they're trying to do? And so I was really excited because I got into fusion to do fusion energy, to make it a reality, to commercialize it for all the benefits for society. And so that's really what this consensus report was kind of about that started off in 2021. So Arturo, your thoughts on it?
You and I have come into the field around the same time, so we had not really been a part of these big processes. And when you look at reports from the past, none of them really did what has been done with these, with the last community planning process, and really starting with the National Academy of Sciences burning plasma process, which was, like you say, can we, how do we get from A to B? How do we get to fusion energy in the grid? And like you say, when we're in grad school, when we're starting our research, we're very focused on the group that you're in, and maybe you hear about all these other groups doing other things. You don't get a sense of the shared mission from the U.S. community as a whole. And I think I agree with you that this was really the first time since I've been in the field that you got this sense of how do we get there, and where are all the things that we really need to, that are still missing. Where do we really need to put our focus in? And it's really great to see the community itself converging towards the needs and where we need to be putting our efforts to.
I was really excited about the aggressive timeline. It actually put a timeline and a date that I could see. So this energy-focused mission that we've been talking about to design and construct a fusion pilot plant by the year 2040, so that's coming up, that delivers net energy to the grid. So we're actually talking about electricity generation and everything that comes along with that on a timeline that can make an impact on climate change too. It's a lot. Yeah, it's harnessing all that, it's focusing on that technology that we need to actually extract power and generate electricity. So that's how we started.
I have a quick question about this foundational story, and we will link to the article that talks about this and lays it out in simple terms. How difficult was this coming together moment? Because it seemed like they were not saying the quiet part of, like, we basically said get in line or go away. And then two, there is the undertone of this potentially came about because of the youths in the movement that are learning fusion and are like, hey, we should do this.
We brought in a facilitator that is trained to facilitate these hard discussions, and I think that was really, really helpful.
And it took a while. The big meetings of this happened right before the pandemic, but all of the meetings were in person, and that, being face to face and having to interact with people that don't do the work that you do, but are making a very compelling case for why the field that they're working in needs to be paid attention to was really important. It's getting everybody in that room and making sure that everybody had a voice was quite critical there.
So it sounds like the key thing to all of the breakthroughs that we're going to talk about was some relationship management at the very beginning that allowed you to present a unified front to the people who are giving you money. I love it. Yeah. Was Fraser involved? I mean, that's
our version. There was polling too. It was helpful.
Lots of polling.
It's really helpful.
All right, I'll stop derailing.
It's fine. So that was the highlight, the first highlight of the year, and that the next came right after that in February 2021, where there was the release of a fast-track National Academies report, and this is building on what is the technology we need to actually construct that fusion pilot plant. And it was focused on specifically designing and constructing this plant to demonstrate electricity by 2035. So again, our community was backed by another aggressive timeline now given by the National Academies.
Something that was particularly new in these reports and these processes versus in the past was the explicit involvement of private industry and how we can actually connect with private industry and how they're part of the community. And we need to be thinking of this as a shared goal, not just what are the labs and universities doing?
Yep. It was also focused again on that commercial feasibility and the market needs. So I was really excited about that to get the market involved. So this is looking at power demands. The model, historically, we go with gigawatt power plants. Maybe future market trends will go smaller and hundreds of megawatt plants, and keeping that in mind. Also keeping in mind the price point. The specific price point has to be met to construct this pilot plant. It needs to be viable to be a commercial entity. So this price point should be less than $6 billion with a projected lifetime of 40 years for this pilot plant. And then they actually acknowledged if we can't meet that price point, you have to go back to the drawing board and look for any technology innovations or advances that can kind of make it marketable at that point.
Yeah. Can I also add that I lead this online Introduction to Plasma and Fusion course at the beginning of the summer for all the interns and for national interns. And I've been doing that for several years, and have had like a narrative of just plasma and fusion, very focused on kind of what we do at PBPL. I got to say that being part of this community planning process and this narrative of what are the challenges, what needs to be in place for fusion to happen, and just what Steffi said, things are not in a vacuum, no pun intended, that there's actually a market that needs to be satisfied. All of this I've included in the last couple of years of the course. It really is a narrative of what is fusion, why do we actually need it, what is the market for it, then some basics of plasma and fusion, and the different approaches and different challenges that need to be done, all very much informed by this process.
And in the lab today, we've been focused on how do you start the conditions to have fusion happen. So all of these reports reflect what do you do next? How do you make something that you can plug into the grid? How do you extract the energy from it? How do you have materials that can withstand these really high heat environments and things like that? So it's tackling those challenges that it identifies that we should do next.
We're at the point where we have reports. Reports have been filed. They've been approved. We have a path forward. And as exciting as these reports are, is there some experimental results that we have to talk about at this point?
Yeah. Well, we can bring up the next couple of months. Here you go. We'll keep moving on the timeline. We're focusing a lot on what's happening in the U.S., so we're going to talk a little bit about what's happening around the world, too, because there's actually a lot of countries that are interested in harnessing the energy from fusion. And so in May 2021, the Mega Amp Spherical Tokamak Upgrade, or MAST-U, sorry, another acronym for a machine.
I love that you started with the definition, right? That is the height of science communication.
Yeah, so this is a magnetic confinement device. It was back up and running after several years of an upgrade. And so they actually were testing out a new exhaust system. So like your engine for your car, you have to pump the exhaust out. That's kind of what we have to do in fusion reactors too, to reduce the heat load on the machine. They have a new exhaust system called a Super X diverter. They showed a 10 times reduction in the heat load. So that was pretty great. That was exciting news.
This is in the UK, right?
Yeah, this is in the UK. Yeah.
Does this help with the downtime? Is that what this really helps with? Does this help with the longevity of the experiment? What is the significance of this 10 times reduction, I guess? So
this is actually a killer in these machines. The fact that ultimately there has to be some heat and particle exhaust coming out, right? So you have to design it in a way that your machine can actually handle this. Now, it's not at the levels of the 10 times the heat of the temperature of the sun by the time it gets to the edge. But nonetheless, there's a lot of heat that needs to be controlled. It really is one of these problems that if solutions aren't found and aren't tested, when you get to reactor-relevant regimes in which you have to maintain a reactor running for a sufficiently long amount of time at sufficiently high temperatures, your machine can perhaps not even handle it. So these solutions are still ways of getting to a machine that can get to the conditions that you need.
Okay, we're going to jump building on another international experiment next. We're going to highlight the Experimental Advanced Superconducting Tokamak, or EAST, in China. Okay, there we go. I defined an acronym. Yes. Okay, so EAST is really focused on studying steady state operation. So this goes to what Arturo was talking about. In magnetic confinement, you want it running for a long period of time. I like to use this analogy that confining plasma with magnetic fields is like confining jelly with rubber bands. It's really complicated, but we're really good at it. What we also need to do is hold on to it and confine it for long periods of time. So in this experiment, they demonstrated in May, they reached 120 million degrees Celsius, or 216 million degrees Fahrenheit. They held on to that plasma for 101 seconds. So that was pretty impressive. And then I'm going to jump ahead because in January, which is right now, they just announced they were able to confine a slightly cooler plasma, 70 million degrees Celsius, for 17 minutes. So this is still a plasma that's 5 times hotter than the sun, holding on to it for these steady state operations.
This was something that I read, and I was like, she's trying to get something over on me here. That's insane. That we're able to contain that amount of heat for any amount of time, let alone like an amount of time that seems way longer than I was ever going to throw out as a potential.
Tell you, magnetic fields are amazing. Magnetic fields, what they do with plasmas, it's counterintuitive because it's right there. You've got, the hottest thing in your solar system, and then a meter away, you've got cryo-cooled superconductors. It's just incredible.
Yeah, that was fascinating. And then another hit the news press. Everyone was talking about it. In August 2021, the National Ignition Facility, or NIF, achieved record-breaking yields. So they're at the threshold of ignition. I just remember talking to my colleagues while they were analyzing the data, and just the excitement they were giving off was amazing. So NIF is an inertial confinement fusion experiment. So again, a scientific experiment that NIF has 192 laser beams, 9 megajoules of energy focused onto a target that has a fuel inside that is 1 centimeter long and 1 millimeter in radius, to kind of compress the fuel down to create the conditions for fusion. Sounds like sci-fi. If you've seen Star Trek Into the Darkness, you've actually seen this experiment because that target chamber for NIF is the one that they use for the warp core of the USS Enterprise.
I think I can just replay the part of me saying, this is amazing. I don't believe this is possible, but it's happening. So just rinse and repeat me just starry-eyed looking at this.
One of the amazing things here is when you're looking at the histogram of like every year, what were the record shots? It's just low, in the hundreds of kilojoules, very low level. And all of a sudden there's a 10-fold jump, right? It's like you're trying to run a 10-minute mile, and all of a sudden somebody runs it in a minute, right? It's just this qualitatively.
Yeah, because if you're looking at the amount of energy they actually put inside that capsule to heat the fuel for fusion, they got 5 times more energy out because of the fusion reactions. So that was amazing.
We're talking about trying to run the 10-minute mile, and then you just get this order of magnitude difference. And I guess my question would be, now that I have 2 fusion scientists that do like experiments and stuff, is that exciting, or is that like, oh man, they're way better than us?
Oh, it's exciting.
Awesome. I was hoping that was the answer.
Yeah, I'm happy for everyone in this field when they do something.
Yeah.
Even if it's not the same confinement scheme that I do. I think, yeah.
And I was going to make this point when we talk about MassU and EAST, the 2 results, the UK one and the one in China, is that, when you see these results, we have scientists that from our lab and from universities in the U.S. that are collaborating with these groups. It very much is an international collaboration. We're all working towards the same goal. We want to get to a point in which somebody says, hey, electricity in the grid made from fusion reaction. Right? We all want that.
Yeah, I think this one was a great testament to it's a lot of different things that come together to make a big result. So it wasn't just one thing that they changed. They had advancements in physics understanding of what was going on, and that was due to more diagnostics or instruments they could actually look at during previous experiments, and then the ways that they're fabricating the little targets too. All these things kind of piece together and modeling understanding to make these enormous accomplishments. And it's just I'm so happy for everyone. So happy. It was so exciting. And that brings us to even more excitement, which happened the following month. I just looking back, I can't believe what happened in 2021.
Yeah, that end of summer.
Right. I'm just going to announce this. This is Commonwealth Fusion Systems, which is, CFS for short. It's a private company that spun out of MIT's Plasma Science and Fusion Center. They announced successful tests of their high temperature superconducting magnet. So Arturo, tell us a little bit more about this one.
As we've mentioned before, the magnetic fields are used to hold on to the plasma. And the stronger the magnetic fields, the more they can hold on to it. This company has been working on using this technology, high temperature superconductors. When you say high temperature, it really doesn't mean, hot. It means not as low a temperature as the normal superconductors. And it turns out that with this new technology, you should in theory get to be able to create higher magnetic fields more robustly if they could develop the magnets themselves. And this was a very big if. When they started this company, the high temperature superconductors were these little threads that you could get a little bit of, but nothing of the length or the technological robustness that you need for a magnet. And this company just worked on developing them, on securing the supply chain, on working with the suppliers, just creating the technology to get there. And in September, they successfully tested a fusion-relevant electromagnet made from high-temperature superconductors at 20 Tesla, which was a record and is of the order of what you need to create these machines. So it was amazing when we heard about this. It was the whole community was just
It's amazing because this allows us, not only does the technology work, but it gives us that option to smaller, more compact reactors. And this is very, important when you're thinking of commercialization, making something that people can actually build.
It is extremely exciting, but I think we've buried the lead on the biggest news from September 2021 in fusion, and that was the very first appearance of Dr. Steffi Deem on the Science Night podcast. You can go back and listen to the episode from September 10th entitled Fusion: Some Like It Hot.
Yes. There you go. You got to plug the back catalog.
With a premium
and really from this point forward, I feel like, we kind of had a hand in all of these next stories that we're going to talk about.
Right, exactly. I threw this one in because it's just like Arturo and I talked about how the U.S. had this aggressive timeline and this plan. We really haven't been able to enact it because of funding. Well, in October 2021, STEP, or Spherical Tokamak for Energy Production, in the UK announces an aggressive timeline. And STEP is their, similar to what we were doing, a pilot plant. So not only has the UK announced an aggressive timeline to demonstrate net electricity generation, they're actually funding it. And they're selecting sites right now. I'm excited for them.
Just to point out, the spherical torus is the type of experiment that Steffi works on is a spherical torus. So
yeah, it's like a more
relevant to this.
More compact.
Like a cord apple. Yeah, like a cord apple instead of a donut. is
exactly.
the typical way that we
more
do
compact
it.
design. Yeah.
It's one of these things of that we're also excited about it. We're like, yeah, well then let's match it. Let's see where we can do.
Yep. And they're also expanding their research and development in technology to actually bring energy to the grid. Then we're going to jump ahead to November 2021, which is the website usfusionenergy.org was launched. I'm going to let Arturo take this one.
Of course, we're particularly excited about this because Steffi and I co-lead this effort. And this came about actually from the community planning process again. When we first started the meetings, there was a thought on how we could improve workforce development. How can we get the public more engaged? And one of the things that many people knew that have been, in the field in the past is that when you Google fusion, you're going to get much more likely you're going to get your Ford than you're going to get, what internships or what jobs there are in the field. So the objective of this site was, can we make it so that we have a stronger presence and easier to reach presence on the web for just the general public and anybody interested in supporting or in joining the efforts or finding out a little bit about it, and making an engaging page, making something that you can tell wasn't made by physicists, something with design, something engaging, and that was the idea of fusionenergy.org. Can we make a one-stop shop for the U.S. For people interested in fusion and to find jobs?
I think the biggest triumph of this entire site is the design. It is so good looking. So 5 stars across the board from this non-fusion person that can look at this site, learn something, and be like, they really nailed this design. This is what's going to actually bring fusion to the door.
And you can tell it wasn't made by physicists.
Oh, you can definitely tell that.
It is gorgeous. I love the team. We work at Sandbox Studios in Chicago, and they worked with an artist too to curate this just for our website too. And it's available for use, for educational use via Creative Commons, all of the images on our website. I also want to mention too, the jobs section, if you look at it, it is amazing how many jobs are open in this field. And I think what was really important to me was that historically our field has just been hiring, PhD level physicists and engineers. And this really reflects where our field is going. To actually harness fusion power, we need a lot of people. This is highly skilled technicians, highly skilled welders, because these are all very custom, intricate build experiments. It's more than just physicists now. It's computer programming, it's HR, it's business plans and things like that. So this is really reflected in that.
And we highlight jobs from universities, from labs, and from companies. We try to make it so that if you are interested in the U.S. in fusion, regardless of which direction you want to go, this could be a place for you to find your job.
Yep. Okay. I'm going to jump to December. This was a big one. This was Commonwealth Fusion Systems announces a $1.8 billion in funding raised. One moment in time, they doubled the private investment in fusion energy.
Yeah, the historical investment.
Yeah. And this is enough to fund Spark, which is their net energy gain device, and also start the effort on the future device after that, ARC. So Arturo, talk a little bit more about this.
I think you've said it all. I can only say that, when we found out about it, we had to check the numbers. We're like, what? Is that B with a B? Billions with a B? It made quite an impact in the community. And it was one of those things of like, oh, now they're set. Now they can build this machine. There's always sort of the uncertainty when these private companies come about of like, can they actually get the support to build it? And it was clear that they can. And, personally, I'm very happy that it was this team, CFS. They're very conservative on their physics assumptions. They have a series of peer-reviewed journals on the physics basis of Spark. If you have to put your money into it, and I think they did, Spark definitely is a good bet. And building a device that can get you to a point in which you break even. The objective of this machine is to do, as Steffi mentioned earlier, a physics break even, in which you have more energy produced by fusion. Energy in the neutrons is a subtlety, but it's energy from the reactions, more energy out than the energy that was put into the system, right? I want to be specific about that. And it's considerably more, enough that you could look into some more physics of what is the physics when the plasma starts self-heating itself enough to get to this next level, right? That's the kind of physics that Spark is going to be looking into, and we're very happy that they're getting the funds to build.
And I love their timeline too. The Spark timeline is set to produce more energy than it consumes in 2025. And this is looking at in a commercially relevant device. I love it.
Again, not electricity in the grid.
Right.
Spark is not going to create electricity in the grid, but it's going to get us it's going to get us much further than
So we talked about this goal of like a break even by 2040 at the very beginning of this. That was a goal, right? And now
of a prototypical plant,
yeah, prototype.
So in a year, that's become not just like a possibility, but maybe like a overly conservative estimate. Is that what I'm hearing? Does that mean the Jetsons like future is just around the corner?
No.
No.
So let's be clear. Spark is not going to get you electricity, right? When we talk about an aggressive timeline to the 40s, that's a prototypical plant that not only creates a burning plasma that's creating the heat that's required, but it's also creating electricity. So when you think of a deuterium-tritium fusion reactors, what you're creating is a boiler, a very expensive boiler. You are creating the heat source so that heat can heat water or heat helium or something, so that ultimately that can turn turbines and create electricity, right? That whole other section of how do we get the energy from the reaction and turn that into electricity, there is a lot that we need to find out about this, and a lot of challenges that need to be resolved. That will not be resolved with Spark. It will not be resolved with ITER. That is something that needs to be worked on still, and that the estimate is to try to get those resolved for a prototypical fusion reactor to create electricity. That's when we're talking about the 30s and 40s.
Got it. I think that was probably an important thing to note and not have me have people thinking that it's really like right down, like you can set an iPhone reminder for it.
I'm glad you asked, because a lot of people, I think this gets missed a lot when we talk about it. So I think it's great that you brought this up so we can make sure it's clear, because it can be, confusing.
It can be confusing, and sometimes, allegations are leveled at our community that we're trying to bamboozle people for this. And it's not true. Sometimes we just get excited about it, and we implicitly think about these timelines differently. But those are
so we're talking about like the big, exciting, like pushing the science forward experiments, not the run of the mill. Fusion energy is so common right now that you're tripping over fusion energy as you walk outside the door. So it's two different timelines.
I can't wait till that happens.
Long for the day.
That would be
great. My final question, now that I'm coming to the end of the time where I have two fusion scientists on the podcast with me, is a really important one. And do you come up with the acronym first, or do you come up with the title first? And is this hotly debated more so than the plasma itself?
I think it goes back and forth. It really does. So I work on this device called Pegasus, and prior to that it was Medusa. And I think the previous PI always wanted to name something Pegasus, so he had to backtrack and be like, okay, Pegasus in Greek mythology came from Medusa. Okay, let's use Medusa and make up an acronym for that, and then I can use Pegasus down the line. I feel like it's a whole intricate plan.
The arc reactor, that is no coincidence.
No.
It's amazing.
That they were able to do that, that's the real breakthrough right
I love it. It's brilliant.
This is coming from somebody whose acronyms are RGDX and PFURO. Like it's just, I cannot do it. You
gotta work on that.
I gotta work on it. They're just
I mean, maybe if you had like $1.8 billion in funding, you could come up with an entire marketing team.
That's probably what we're missing right now.
That's my pitch right now. Yeah. Come on, Bill Gates. We could make some great acronyms.
King of the acronyms, right? Steffi and Arturo, thank you so much for guiding us through the year in review in fusion energy. It's been really exciting, but I think we would be missing a great opportunity as the Science Night podcast if we didn't interview someone who engages the public with fusion energy. And that is a person who's here right now. So Arturo, how about you and Steffi just like talk about what you do for a little bit? How's that sound?
Absolutely. I'd love to.
It's so much fun. I love it.
We will have that conversation after this quick commercial break.
Hi, I'm Matt.
And I'm Phil.
And together, we host the History's B-Side podcast.
You know, history is full of amazing stories and memorable people.
But we don't care about them.
Every week, we break down history's biggest stories and the forgotten people who made them happen.
We're not historians. We're just two guys who enjoy a great story and plenty of laughs.
Find us on Apple Podcasts, Spotify, Amazon Music, and more.
Or follow at History's B-Side on Facebook, Twitter, Instagram, and YouTube.
This is History's B-Side.
Okay, welcome back to Science Night. Dr. Arturo Dominguez is a physicist and an innovative science educator. He's also the head of the Science Education Department at the Princeton Plasma Physics Laboratory. There's a lot of other things you do, Arturo. I'm going to throw in there co-leader of the U.S. Fusion Outreach Team, co-leader of usfusionenergy.org, because those are kind of my favorite things.
Yeah.
But, okay, tell us what you do, Arturo.
As you said, I'm the head of the Science Education Department at the Princeton Plasma Physics Lab. Our department focuses on outreach, on workforce development activities, both locally and nationally and internationally. So it's a very diverse job, and we get to do a lot of innovative stuff.
So let's dive into a little bit about how you engage the public and educators.
It's a lot of different ways that we do it. We're in Princeton, New Jersey, between Philadelphia and New York. One of the ways that we do it is just engage with the local schools and with the local public and let them know that we exist, that we're around, that there's some interesting stuff that's going on in the labs. And we coordinate with the local staff and students to get them to go to schools and talk at the schools. So that's one way that we do it. We've developed some really cool demos that can be both used in person but also online. And so we've developed some tools that we can use online to play with plasmas, to learn about fusion. So that's another way.
You have to tell us about that online tool that you have where people can actually log in and control a real plasma in the lab.
Yeah, so I came into the lab 10 years ago, and one of the first things that my boss, Andrew Zucker, tasked me with was we have this, what's called a DC discharge, which is just kind of like a fluorescent light bulb in the lab. And he said, we want to put this online and make it accessible to everybody. And I was totally on board, and with the help of some really talented high school and undergraduate interns, we got to work. We made everything controllable through these computer-assisted tools. This particular program called LabVIEW, which is just something that you can control scientific equipment with, made a full online interface and launched it. And it's available to the general public. Nothing, you don't have to have any special VPN or anything. and you just go in and control an experiment from anywhere in the world.
So what's the website where people can go to control this plasma?
Oh yes, so it's called the Remote Glow Discharge Experiment. So I know it's a handful, but so it's RGDX, and we'll put it on links. We'll put it somewhere because it's a little
we can
hard
put
to
it on the
audio.
show notes.
Yes.
Yeah, we can do that.
Yes.
Okay, what are other ways you engage the public or education? You said workforce development is part of what you do as well.
Yeah, so outreach, the more accepted term now is public engagement, because outreach is very one-directional. We really do want to do public engagement in which we're interacting with the public, but also it's a bi-directional thing. We want to learn from the public what it is that they're concerned about. And actually, this is going to be something that we will talk about a little bit later about fusion. But, public engagement is really going out to the public and sharing what we have, but also getting feedback from the public about their needs and their interests. So we do a lot of outreach or public engagement, but we also do workforce development, which is the engagement with the public is longer. And the idea is to trying to give students, mainly students, an opportunity to learn about STEM research, but also about plasma and fusion, ultimately with the goal of trying to make our field welcome and trying to bring in our next generation of scientists and engineers to help us tackle all the challenges, both physics and engineering challenges that we have for fusion and for plasmas. So we have a lot of workshops, for example, at a whole bunch of different levels, at early undergrad, at more advanced undergrad, connecting to internships, to faculty members, primarily at minority serving institutions, at graduate level students. So we tap into the resources both at PPPL and nationwide and even worldwide, and make workshops and make summer schools for students and for the general public to learn about the challenges and to get them a little bit more prepared and to try to decide to go into the field.
And some of those materials or those workshops, the general public can log into, right?
Yeah, so we've always been very much focused on what can we make available to everybody, right? And this is not only in the outreach side or public engagement side, but also with the workforce development. As you just said, the summer schools and the workshops, we make them available to the public as much as possible. We have websites which we'll also share. We've got a bunch of websites, which we'll also share with your listeners on, the lectures that have been given in the past 5 years in the Introduction to Plasma and Fusion course. You have literally hundreds of hours of excellent content, lectures delivered from researchers from all around the country and the world. There in this site, organized in a narrative that makes sense to us of plasma and fusion and challenges of those fields.
Yeah, you mentioned, not only the lectures that you are a part of and the workshops, but also hands-on experiments. And I really want to know, what's your favorite hands-on experiment that you use in your work?
The DC discharge, the one that we're talking about RGDX, that, I gotta say that's my favorite. Now, it's the one that I work on the most. That might be biased then. But what I really like about it is that it's really just a glass cylinder with normal air, nothing special in it, in which we take a lot of the air out, we put it under vacuum, and then we put a large voltage, about like 1,000 volts, across the gas tube, and it creates a plasma. Like it right away creates a plasma. And just with that very simple setup, you can study a lot of things. You can study the relationship between how much voltage you need to turn it on versus the pressure and the distance between the electrodes where you put the voltage. And that's very relevant to understanding, for example, why you need such high voltages for lightning, or what's the optimal pressure for fluorescent light bulbs, or why, if you want to do medical applications for plasmas, you need very small distances. Like a lot of these things can come out of this very simple and inexpensive experiment. And then if you start putting in a little bit more hardware in it, you can learn some really important tools that we use in fusion experiments that we use at more advanced experiments, but you can do it in this small experiments like probes or spectroscopy.
I'm just going to jump in here. A probe you can stick in the plasma. You can actually measure characteristics. Spectroscopy, You're looking at light emitted from the plasma to understand more about it.
Yes, thank you. Yes, that's right. And this is, as you know, this is something that's used in fusion relevant experiments every day. And so it's a great way to get people knowledgeable about the basics of it.
So yeah, I would agree. That is my favorite. I do log onto that website, just to get a chance when I'm missing my own experiment because we're down. Now let's switch a little bit to, you do a lot of work with engaging the public. How did you get to this position? What's your background that kind of led you here?
Yeah, it's, so that's a good question. I started out in a typical research career path for a fusion experimentalist, plasma physicist. I actually started in Bogota, Colombia. I'm a native of Bogota, of Colombia. I started studying physics there, and I transferred halfway through my undergrad to the University of Texas at Austin, hook 'em horn. You're contractually obligated to say that. I finished my undergrad there, and at the last couple of years, just out of serendipity, I learned about fusion. I had a professor that I really wanted to work with, and I worked in his lab with his group. I worked there. I helped build a machine there and got excited about fusion. And then I got into grad school at MIT, where I worked in experimental plasma physics and worked on the Akator CMOD tokamak there.
What's a tokamak?
Ooh, yes, Akator CMOD tokamak. So the tokamak is a fusion device. It's a big donut-shaped metal container in which we create a plasma to temperatures, hotter than the center of the sun, and that's where we try to do fusion. On Akator CMOD, I worked on a diagnostic. We call it diagnostic. It's really just an instrument that you try to measure things of the plasma or the machine called reflectometry, which is it's kind of like a radar. You send in electromagnetic waves, and they bounce back at different densities in my case, and you can tell a little bit about what's happening where it bounces back. And that was some really interesting work. We did some studies on these fluctuations that arise in the plasma. My undergrad and primarily grad school, I was doing a lot of public engagement. At the big conference, I would always do outreach at the Plasma Expo, and I would give tours. I was just very involved in that side of it. And when I was finishing up, I saw a postdoc position open up here where I'm currently working for a postdoc in the science education department. And when I saw that, I'm like, I didn't even know that was a possibility. I was just, when I saw my, 5 years from graduation, I would just see myself doing research in either a lab or somewhere like that, which would be fine. I love being able to do it, but I really felt that I was very well suited for the outreach side. So I started conversations, and it just worked out.
I will say I've been to conferences because we work in the same field. So I've been to conferences with you, Arturo, in the past. And it is inspiring to see how many students are in our field because of some outreach event you did, or Sully, the summer school too. So that is just really impressive. And it really speaks to all the work that you do and the innovation that you do.
Thank you for saying it. I feel the same when I see people and they tell me, or I see them that I've known that they've come through some of our programs. I feel like it just supports the fact that I'm doing what I want to be doing, what I need to be doing, because it really is impactful. Like you see these people that you've had some sort of impact. Not necessarily that because of you they decided to go into the field, but at least that you were able to engage with them and maybe help sway the needle towards the field, and I love that. That's really it's really great.
It's really great. And I know it's a lot of work too. So what do you do in your free time to get a break from all of this?
So I've got a 4-year-old, which is to say that it ends up being not that much free time. And I've got a very high maintenance dog who also takes a lot of our time. A lot of it is family stuff. I like to salsa stuff. I'm trying to get my son to learn how to dance and to get engaged with Latin and particularly Colombian music. So we do a lot of like just running around wild in the house.
That sounds amazing. And I've actually witnessed some of it during our Zoom meetings.
Yes, you have. And he's slightly hyperactive, so.
It's a lot of fun. It's a party. I always look forward to meetings with you for that reason. So just to kind of close it out, you mentioned it's a non-traditional kind of path for the way we're educated. If there's anyone that's asking you, like, how do they get into what field you work in, where it's public engagement, it's workforce development, what kind of advice would you give them?
That's such a hard question. And it's such a hard question because I run into this all the time. It's a good thing that it's been happening more and more because I feel like it's making an impact and people are like liking the outreach and the engagement. Unfortunately, there's not a lot of set paths forward for it, right? I was very lucky to find that postdoc. I'm glad to hear that other big labs and institutions like D3D have created an outreach department there, public outreach and engagement, and the colleague there is amazing, and we're very glad that that's happening. And I know that there are some other labs, but not necessarily in plasma infusion labs. There are some of these opportunities. I think that what really helps me the most, I'm going to speak very selfishly, what really helps me the most are people like you that are doing research, that are in the field, that are actually educating in the research, but very much engaged in the public engagement side and the workforce development side. And having partners like you all around the country, the value, creating a podcast to reach people on about these topics of science, right?
Well, that was all James here, so we got to thank James.
But giving talks at seminars and going to the Conference of Undergraduate Women in Physics and talking about plasma infusion, all of these things are really the most impactful way of engaging, right? Being in there. I hope that's not a cop-out, but I think that's, I really
no,
think
it's good.
Those are my best partners.
Well, thanks so much, Arturo, for joining us. It was so great to have you here on Science Night.
Thank you for having me. It's been a pleasure.
That is the end of the Science Night Festival of Fusion. My name is James Reed. If you want to follow me, go over to Twitter. My handle is @James_Reed3. Steffi, where can everybody find you?
You can all find me on Twitter @SteffiDeem.
And Arturo, where can the kids find out what you're doing?
Thanks, James. Yes, you can also find me on Twitter at ArtDomi. So I'm Arturo Dominguez, so it's @ArtDomi. And you can find the one tweet a month that I post there.
Perfect.
Awesome. And we will have links to all of the other things that Arturo does over at our website, which is @scinight.com. That's where you can find all of our past episodes, all of the links to our social media, and all of the fun things that we are doing with this podcast and with this brand. And hey, Since you've taken the time to listen to this podcast, why don't you give us whatever the highest review is on your podcatcher while you're doing it? Because that is what helps us break through the noise in the podcasting world. So give us 5 stars, a thumbs up, whatever that happens to be. We will be back in 1 week with a regular episode. And until then, have a great night. The Science Night Podcast is a proud member of the Riverpower Podcast Mill. To find out more about our shows, go to riverpower.xyz.